Hello, everyone. This is the lecture video for Chapter 8, Lecture 1. So we're starting a new chapter, and we will spend 2 days on it. So Chapter 8 is on the quantum mechanical model of the atom. So in this chapter, we're going to look at waves, and then we'll go into a little bit of quantum chemistry, and you guys get to learn, what is the quantum mechanical model of the atom. We're going to be talking about orbitals, and things like that. All right. So the main ideas of quantum mechanics. So quantum mechanics is, relatively new branch of physics and chemistry. And it's because the quantum world was kind of invisible to us before, right? It was our always existed, but we were like blind to it, right? Because it's a really, really small world, and we weren't aware of it until we had sort of the know-how and the technological advancements that allowed us to detect this small world and to learn more about it. So before that, we had the macroscopic world, right? And so when I'm talking about the macroscopic world, just think, the large particle world that we're in, and then the quantum world would be like the tiny matter, right? And how tiny? We're talking like electrons and protons, right? Um, Things that you can't even see using a microscope, right? It's way down there. So that largely that quantum world was, inaccessible to us, and it's still a lot of it still is, and we're just, still learning about it. However, with the discovery of the quantum world, we've been able to advance society so far, right? And so it is it's a very real thing, um, and it has a big impact on our world. So before we knew about the macroscopic world, it's called the large particle world. And in the large particle world, everything is deterministic. And what that means is that the present conditions will determine the future. So if you know the present conditions, you can predict what's going to happen in the future. Um, and the most, important one is that particles exist in only one state. What that means is, if I'm here talking to you, that means I'm not at home, right? And I'm not at the store. I'm at school, and therefore I'm only existing in this one state, right? Well, the quantum world is kind of opposite, right? It is first you have really, really tiny particles, like electron level, atomic level, electron level, proton level. And in this world, things are non-deterministic. So the present does not necessarily determine the future. And that's really crazy to us, right? Because that's not how we operate. We do not experience life non-deterministically, right? And so that's one of the reasons why it is so hard for us to understand this world. And also why chemistry is so hard, right? Because chemistry belongs in this world. So there, in this quantum world, particles can exist in dual states. Okay. So that's like saying I'm not I'm talking and I'm not talking at the same time. Like, what? That doesn't make any sense, right? But that's exactly what a dual state is. And so absolute small particles like the electrons can be in two different states at the same time. Okay. So that's like saying I'm here and I'm at home at the same time. That doesn't make sense, but in the small particle world, that's what happens, right? So, something like an unobserved radioactive particle is simultaneously emitting and not emitting radiation at the same time. And the only way for it to collapse into one state that we can understand is for us to measure it. So as soon as we measure whether it's emitting or not, you force it into one state, and we of the larger particle world will only experience it in one state. We'll only see us in one state. Okay. And that's crazy, right? So we can never really directly observe, we will never be able to directly observe um, a particle emitting radiation and not emitting radiation at the same time. Right? Um, so, the way I think about it is, we're too big, right? We're too The particle world, the small particle world, is too fragile, right? And so, we're kind of like too dumb to like understand the quantum world, and so we just don't perceive it the way that it is. So Schrodinger, one of the grandfathers of quantum mechanics, while trying to relay, what he's found about quantum mechanics to his peers and the wider scientific community, came up with a thought experiment to explain what quantum mechanics is. He says, just imagine that there's a box and inside is a cat. And also this mechanism that if it is triggered, it will break a flask full of poison that will kill the cat. Okay. And that the mechanism can be triggered by this very small radioactive particle that is, remember, both emitting radiation and not emitting radiation at the same time. So when the box is closed and the cat is inside, the cat is both alive and dead at the same time if you keep the doors closed. But as soon as you open the door to see, oh wait, I want to see what it looks like if a cat is both dead and alive, all of a sudden, that duality will collapse into one reality, right? One observation. Either the cat is dead or alive, but not both, right? So us tampering with the quantum world kind of collapses it, right? It no longer exists in its actual, natural state. And so that's why chemistry is so hard, right? The electrons, which govern everything around us, govern matter, is part of the quantum world. And in order for us to understand chemistry, we have to understand the electron behavior. And we can't, really understand the electron behavior because it's so tiny and its physics is very different than, the physics that govern our bodies, right? In the macroscopic world. So this, revelation and this discovery, right, that the electrons, this quantum world behaves so differently and the electrons can exist in dual states, just shocked everybody. And so this is what they said about it. Niels Bohr said, anyone who is not shocked by quantum mechanics has not understood it. Schrodinger wrote, I don't like it, and I'm sorry I ever had anything to do with it. And Albert Einstein says, God does not play dice with the universe. Okay, so let's look back a little history of how quantum mechanics came about. So until the beginning of the 20th century, it was believed that all physical phenomena were deterministic, right? And we call this classical physics, right? So as in, if I have a cannon and it's at this angle and it's going to shoot a cannonball out at this speed, where will it land, right? And so those kind of problems, you would learn about in physics class, you are able to very precisely predict where that cannonball is going to land based on the conditions that were given to you. So again, deterministic, right? The present conditions will determine the future. And we know that physics very, very well, right? We're able to predict very precisely those kind of things. But work done at the time by a lot of the physicists that were then studying subatomic particles, which are a lot smaller, realized that the present condition did not determine the future condition. And those people were Einstein, Bohr, Louis de Broglie, Max Planck, Heisenberg, Dirac, and Schrodinger. These were the fathers of quantum mechanics. They realized these subatomic particles do not behave like, the macroscopic particles in our world. And the reason is because they are extremely small, okay? So electrons, right? In chemistry, we care about the electrons. Well, electrons are part of that quantum world. They are incredibly small. So a single speck of dust has more electrons than the number of people who ever lived on Earth, okay? So imagine how small that is. And because it is so small, its behavior is nothing like what we would expect, right? Of say like a marble or a baseball, right? And because the electron behavior determines so much of how atoms behave, we do need to understand it. but it's hard to do so, right? Because observing the electron directly is not possible. And so we can only observe the electrons indirectly, because even just shining a light on the electron would affect its true behavior. Okay. Um, so the theory that explains electron behavior is called the quantum mechanical model, and it explains how the electrons exist and behave in the atom. Until up until we had quantum mechanical model, we didn't know a lot of things. We could not explain a lot of things in chemistry. Like, for example, why some elements are metals, why others are not metals, why some elements gain one electron while others gain many, or they lose electrons, right? Why some elements are very reactive while others are not. And then why do we see certain periodic patterns that we do? We just couldn't explain those things. We were able to observe it, but we didn't know why. It wasn't until quantum mechanics came along that we were able to explain these things. And that was very, you know, uh, revolutionary. Right? So, so here's a summary, right? Before quantum mechanics, we had classical physics, and classical physics said, matter is particulate, matter has mass, energy is continuous and wave-like, and energy has no mass. Then quantum physics came along and kind of turned everybody on its head, right? And it said matter can also be non-particulate, matter can be wave-like, energy can be particulate and discontinuous, and energy also has a mass, right? So it kind of like muddled the lines between what is matter and what is light, right? We know matter is anything that has mass and has a volume, but light, as you can see, seems like it's massless, right? It's just rays of light, and those are waves, right? So quantum physics allowed us to kind of change our perspective and be like, no, actually, there's a duality in everything, including light and matter, and there is a relationship between light and matter. They can be both, right? Matter and energy can have similar properties to each other. And so the way that I think about it is, if you have a spectrum, and at the very left side, you have very small and very light particles. These tend to travel very fast. Okay, and so if you think about the speed of light, that's really fast. That's because it's not very heavy, right? But in the macroscopic world, where you have heavy particles, we travel very slow. So even the fastest, things that travel at 100 miles per hour, 1,000 miles per hour, that's still considered slow compared to the speed of light, which is 3.0 times 10 to the 8th meters per second. Right? So this is the world that we've been operating in. And we realize that there's this whole spectrum, and the ones that are on the other end of the spectrum behave very differently. Okay? So here we have non-deterministic, and here we have deterministic. Okay? So the physics that govern these two worlds are very different. Okay, and so as you go down, okay, in being less massive, you start to be faster, right? And once you're faster, it gets complicated to figure out the position of these particles and how fast they're traveling. Okay. And that's actually what makes it very, very complicated to study the quantum world. Okay, so again, quantum physics says matter can be wave-like and energy can be particulate or discontinuous. And energy can also have a mass. Right? Okay, so in order to understand it better, right, we have to understand the nature of light first. So what is a wave? Matter we are pretty experienced with, right? But light, not as much because they're mostly invisible to us, right? So light is a form of what's called electromagnetic radiation, and it's comprised of perpendicular oscillating waves. One is the electric field, and one is the magnetic field. The electric field is a region where the electrically charged particle will experience an attraction, and the magnetic field is where magnetized particles will experience attraction. All of these electromagnetic waves move at the same rate, right? At the same speed, and that's called the speed of light. And you guys should know this number, 3.00 times 10 to the 8th meters per second. Okay, so this is what it looks like, right? There's the electric field component, which is in red, and then perpendicular to that is the magnetic field component. And the thing about light is that if there's an electric field component, there has to be a magnetic field component. So you cannot separate these two. They will always be coexisting with each other. So if you somehow create a magnetic field in the lab, you will induce an electric field along with it, and vice versa. If you create an electric field, then a magnetic field will get induced as well, right? So they go hand in hand. Right? Now, the speed of light is so fast, and you guys have probably experienced this before, that in a storm, you hear the thunder before you see the lightning before you hear the thunder, right? And why is that? Well, light travels a million times faster than sound, right? Sounds at 340 meters per second. That's times 10 to the second power, right? 3.4 times 10 to the second. Well, speed of light is times 10 to the 8th. Okay, so you see the lightning way before you hear the sound, right? Okay, so let's go and look at the anatomy of a wave so that we can understand it better. So uh, the first characteristic of a wave that you might have noticed is the amplitude, right? Which is defined as the node to the crest. So the amplitude basically measures the height of a wave. And you can imagine waves in the ocean, right? If you been in the ocean, you know what a wave shape looks like. So the amplitude is basically the height, and the wavelength is the measurement that's covered by the wave. So crest to crest or trough to trough. Okay, so it's gonna look like that, right? So the amplitude is the height from 0 to the peak, or you can even measure it from this neutral 0 line to the trough. Okay, and the wavelength is either crest to crest or trough to trough. Okay. Another characteristic of a wave that you should know is called the frequency. The frequency is the number of waves that pass through in a given period of time. So let's say the window of time is 1 second. You can measure how many crests have passed through in that 1 second window, right? And the total energy of a wave is proportional to its amplitude and its frequency. So if you want to know the energy that a wave carries, you have to consider both amplitude and frequency. Of course, the larger the amplitude, the taller the wave, the more force it's going to have, right? If you experience ocean waves, you know that. And then, of course, the more frequently the waves strike, the more total force there is. So that's more energy too. So again, the higher the frequency of the wave, the more energy, right? And then the higher the amplitude of the wave, also the more energy that it carries. The frequency of a wave is measured in what's called a hertz, and that's abbreviated as capital H, Z, and it is equal to 1 inverse second. So it's just basically measuring cycles per second, right? So from crest to crest, we can consider that as 1 cycle. Okay. So 1 RPM, right? If you think about your car, 1 turn of a wheel is also 1 cycle, right? So it's the same thing with the wave. So 1 cycle is on top, right? And then the denominator is per second. So that's how you measure frequency. So if you have more cycles per second, that's a higher frequency than fewer cycles per second. right? So now, because all waves travel at the same speed, okay, then what that means is the shorter the wavelength, the more frequently they pass, right? Just think about that, since they're traveling at the same speed. So if they have shorter wavelength, more peaks will pass, and therefore you have a higher frequency. So that means you get this equation here, okay? Let's go to the board for this. It's easier. So c is the speed of light, okay? And it's a constant, right? And you have lambda and nu. Lambda is your wavelength. So these are new symbols that you guys should learn. And then nu, you write it down too. So these are Greek symbols. So nu stands for frequency. Okay. So think about this. If wavelength times frequency is equal to a constant, that means that if wavelength decreases, frequency has to increase for them to multiply to each other to equal to a constant, right? So lambda and nu, wavelength and frequency, has inverse relationship to each other, right? So the shorter your wavelength, the higher your frequency, and the longer your wavelength, the lower your frequency. Okay. And you can see that from this picture here. Okay. Let's look at the picture on the left. And let's say this is a window of time of 1 second. Okay. So you see that the blue light down here has more peaks that pass through that window of time of 1 second, right? So the blue light, we say, has more frequency, higher frequency. And this reddish orange light here has lower frequency. Okay. But why does it have lower frequency? Because its wavelength is longer. So fewer crests will pass in that same amount of time, right? Does that make sense? And so that's how it goes. When you have high frequency light, that means you have a shorter wavelength of light. So blue lights have shorter wavelength, whereas red orange light has longer wavelength and has lower frequency. And then of course the yellow light is in between, right? Somewhere in between. And so that's how it goes, right? Inverse relationship between wavelength and frequency. Now, amplitudes, if you have higher amplitude, that means you're gonna have a brighter light. Lower amplitude is a dim light. Okay. So you can see how these light manifest to our eyes, right? Amplitude is dialing in the brightness, whereas the frequency and wavelength gives us colors. Okay. So if you see a blue light, it's because it has shorter wavelength. If you see red light, it has longer wavelength and lower frequency. Okay. So let's use that equation that we just learned, right? Calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th inverse seconds. Okay, you see that inverse second is the unit of frequency, and it's asking for a wavelength, right? So let me write that down. U is equal to 4.62 times 10 to the 14th inverse seconds. And remember, our equation is C is lambda times nu. Okay. We are asked to solve for wavelength, so we are asked to solve for lambda. Lambda is equal to C over frequency. Okay. And then C is the speed of light, right? Just a constant. It's the same every time. You gotta memorize it. 3.00 times 10 to the 8th meters per second. You divide by frequency, which is given to us as 4.62 times 10 to the 14th seconds. And let's see how the unit works out. Seconds. And this is 1/2 so that cancels. Okay. And then we just have meters left, which is a unit of length, right? All right, so let's punch that in. 6.49 times 10 to the 7 meters. Okay, you guys getting that too, right? But it's not wanting it in meters. It's asking for us to give it in nanometers. So now you guys remember your prefixes. Okay, meters to nanometer. Remember, there's in 1 meter, 10 to the 9 nanometers, or 1 nanometer is equal to 10 to the minus 9 meters, like however you want to remember it. Okay. So 1 meter on bottom and 10 to the 9 nanometer on top. That's how I like to remember it. And so this turns out to be 9 minus 7, which is 649 nanometers. Okay. Okay, good. All right, let's do this one too. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometer. Calculate the frequency of the light. So this time it's giving us wavelength and asking to solve for frequency, right? 515 nanometers. What is the frequency of the light? Okay, so we know that since the c, speed of light, is in meters, we need to change nanometers to meter, right, to make that unit match. So in order to do that, again, right, remember 10 to the 9 nanometer in 1 meter, right? So 1 meter on top, 10 to the 9 nanometer on bottom, and that's going to give us 5.15 times 10 to the minus 7 meters. Okay, and then we're solving for frequency, right? So we're solving for nu, and that's how you write nu. It looks like a V, which is a hook. Okay, that's what I do. Just draw a V and then with the hook. So C over lambda, right? Easy algebra. That's equal to 3.00 times 10 to the 8 meters per second. Divide by the wavelength, 5.15 times 10 to the minus 7 meter. Meter cancels, and look at what we have. 1 over second, that's the same thing as inverse seconds, right? Which is a unit of frequency, so perfect. So we get 5.83 times 10 to the 14 inverse seconds. Okay, so easy, right? This is the equation that allows you to do that, right? To convert between wavelength and frequency. And remember, they're inversely proportional, right? So the higher the frequency, the lower the wavelength, and so on, right? The shorter the wavelength, the longer the wavelength, the lower the frequency. All right, so let's talk about color. Okay, how is it that we see color? So remember that color of the light is determined by the wavelength of the light or the frequency of the light, and it's on a spectrum. So have you ever seen the rainbow? And you know and if you notice, it's always the same order of color, right? And the rainbow is always going Roy G. Biv. That's how I remember it. Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And that's the spectrum. So why is it that we see color? It's because the light, okay, white light is light of all colors, okay? And when white light hits, say, this pigment on my shirt right here, that's orange, this pigment is absorbing a complementary color of orange, okay? Or it's absorbing every other color but orange. So the orange gets reflected to your eyes, okay? So the, depending on the pigment, right? And here the pigment is red. So that means this pigment right here is absorbing all other colors but red, or it's absorbing the complementary color of red. Okay. So if you guys remember back to kindergarten, let's review kindergarten, right? You have the color wheel divided up into 6 pieces here. And we go Roy, G, Viv. Okay. So this is how it works. If something is red, it is because it's absorbing green, the complementary color. If something appears orange to your eyes, it's because blue is being absorbed by that thing, right? If something appears purple to you, that's because that material is absorbing yellow light. Okay. So that's how, I would remember. Just if you know how to draw the color wheel, you'll know what the complementary colors are, right? Now let's add a wavelength to it. So remember, violet light, blue light, and violet light had the highest frequency and therefore the shortest wavelength. So that's going to be 450 to 700, which is red, right? Red had the longest wavelength, and so therefore 700, right? So around here is 550. These are nanometers. So if you guys, can draw the color wheel and kind of remember the wavelengths, it's going to be really helpful for a lot of the calculations in this chapter. Alrighty. So let's look at the entire electromagnetic spectrum. Okay. So it's quite wide, as you can see, and the way it's arranged on this slide is low energy, low frequency on the left, then to high energy and high frequency on the right. Of course, because wavelength is inversely related, it's going to be arranged from longest wavelength to shortest wavelength, right? Okay, so let's go from left to right and explain what is each of these waves on these electromagnetic spectrum and what do they do, right? I'm sure you've heard of the radio. So radio waves are the longest waves, as in they have the longest wavelengths, right? And so that's why they're used in radio, TV, cell, because they're able to reach long distances because of their long wavelengths, right? So that's the technology we use radio waves for, right? It's telecommunications. And then next up is the microwave. So microwave has a slightly shorter wavelength than radio. And what do we use that for? Warming up food, right? And so how does that work? Microwaves basically activate the OH bond in water. And when OH bond gets activated, it vibrates, and this vibration creates heat, and that's what heats up your food. So, a lot of your food have water in it, right? So when you put it into the microwave, zapped it with these waves, and it's exciting the OH bonds in the water in your food, and also the water vapor in the microwave. And that's what heats things up then, right? Okay, and then the next one up, infrared. You guys might have heard this. Infrared is used for night vision. So these night vision goggles, what they're doing is they're picking up infrared waves that are given off by heat bodies. Okay, so bodies that give off heat have this signature infrared wave, and these goggles pick them up, and so that's how you're able to see at night. And then after that, you have the visible spectrum. The visible spectrum is, what we see, right? We see colors. We don't see radio, microwave, or infrared. They look invisible to us, right? Because we don't see in that region. So here's our sort of narrow range of where we can actually see, so we can discern colors. And so we're discerning 750 nanometers to 400 nanometers. Okay. And that's what I mentioned earlier, right? The short wavelength one is purple, the longer wavelength one is red. And I want you guys to actually memorize this, okay? I want you to memorize the rainbow, Roy G. Biv, and I also want you to know roughly, not exactly, but roughly where, what wavelength each color is. So if you know that red is at 750 and you know that violet is 400, then you know that the green and yellow regions is around 500 or 600, right? And so that makes it also easy to guess where orange is and where blue is. So just roughly where, what are the wavelengths of each color of light, right? Because that's our world, right? So you should know that. Okay, so again, the shortest wavelength and the highest energy light is purple. The lowest energy light and the longest wavelength is red. Okay. Okay, then after that, we have ultraviolet, right? So ultraviolet is more energetic than violet. That's why it's called ultraviolet. And that's like the waves that are given off by the sun, right? You have UV, A, B, C rays that are coming from the sun, and it's very energetic, and it can burn you, right? You guys probably suffered from sunburns before. It's not fun. If we were able to see ultraviolet, maybe we'd be like, oh, wait a minute, we need to get out of the sun, but it's invisible to us, right? It's outside of the visible spectrum. So we feel it, but too late, right? By the time that time, it's too late. And because it's energetic, it could cause skin cancer if you are exposed to it, chronically, over time. So that's why you want to wear sunscreen, right? So now going up more energetic is X-rays. X-rays way more energetic, and you guys know what that's used for in the doctor's office. Um, they're trying to like see past soft tissues, right, into the bones and stuff like that. You can use X-ray for that because X-ray is really energetic and penetrating, so it can penetrate past those tissue, right, and see into your body. Back in their day, they didn't even have these. Now they have these lead protective coverings for your body. Back in the day, they didn't have that. So, trial and error. So after a while, they're like, oh, these people got cancer from going to the doctor and getting a lot of X-rays. Okay, maybe we should offer, these lead vests for protection from the X-rays, right? Because you're really getting up there. Now, once you get up to gamma ray, that's the highest energy wave, right? It's the highest energy light, and that's basically like a laser, right? Gamma rays are so energetic and so penetrating that it can actually kill cells, right? And so it's often used in chemotherapy to direct these beams, high energy beams, to kill cancer cells. But the problem is, it's not super directed, so it can also kill healthy cells around the cancer cells as well, and then tends to make you very sick, right? It makes the patients very sick. Okay, so white light, right? When you go outside, you look, up at the sky and you see light, it's not of any color, it's colorless, right? Or you can call it white light, right? These white light is actually a combination of all the colors. So if you take Roy G. Biv and you mix it together, it'll look white, okay? And only when it's passed through a spectrum, it's passed through a prism, sorry, that you can see the spectrum of light that we call the rainbow, right? So that happens. You know how a rainbow happens? And why it's actually a bow? It's because it gets passed through little tiny droplets of water. And so that's why you see rainbows after it rains, because you have these little droplets in the air, the little mists, and sunlight gets passed through these droplets, and the droplets act kind of like a sieve, like in your kitchen, you have a sieve. Well, it's a sieve that separates these individual colors apart, right? So that you can see the rainbow. And why is it a bow? Well, because droplets of water are curved, right? And so when it gets passed through this curved droplet, it bends, right? And so that's why you see it in that formation. Pretty cool, right? So color blindness. This can, that you have actually rods and cones in your eyes that perceive these wavelengths so that you can perceive different colors. And some people, for some people, it's damaged, right? The rods and cones are damaged or something is missing. And so that they're unable to see colors. And so what they would see is more, people say it's like red, red-green colorblind, so they don't see that. And so they see, very kind of grayscale, kind of what dogs and cats see, as you can see in the right picture. It's a lot less vibrant, right? You don't see those red colors. Okay, so here's an image just for you. This is using infrared light in order to detect heat signatures. So these you can see in this image where it's blue is where there's no heat, so that's like cold environment. And then where you see the red would be the hottest environment, right? And of course yellow is warm. So you can see that where the red are is on the bodies of heat evolving things, right? Like humans and dogs. And you can see where it's most red is the face, right? The legs, the eyes, the ears, right? You see that the fur on the dog does not have heat, so it's blue, right? So this is what allows you to see in the dark um, uh, 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 by using infrared, right? So you're picking up heat signature. All right, this is a picture of a tumor being killed by radiation, by gamma rays, right? Remember, gamma rays are the most energetic rays, and they're more able to be directed, like a laser. And so it shoots at the tumor and kills the tumor. However, of course, you always have some collateral damage because it can also, kill some of the healthy tissue around the tumor, and that's why a lot of the patients get sick when they go through radiation therapy. And that's also why you have hair falling out, right? Because you basically have damage of this healthy tissue. Okay. Next, let's talk about interference. So waves and light, they can do what's called interference that matter can't do. Okay. So waves and light, they can either go through what's called constructive interference or destructive interference. Constructive interference is when the waves interact so that they add to make a larger wave. This is called in phase. A destructive interference is when the waves come together, trough to uh, no, trough to crest, and they cancel each other out. So it is called out of phase. Right? So it looks like this. When the waves are in phase, right, the crests meet up with the crest, and it's just addition. Okay, it's just addition and subtraction. That's it. So, you can see that if this amplitude here is 5, and this amplitude is also 5, then when you add these waves in phase, this new amplitude is 10, right? So that's why we call that constructive interference. Now, when the waves are out of phase, then, okay, let's say the amplitude here is 5 again, but here you have a trough, so that amplitude is -5. So what happens when you add them together? +5 and -5 cancels it out. And so that's why we call this destructive interference, right? When the waves are out of phase. Okay. Now, matter don't do this, right? So that, just comparing the difference between a wave and matter. Like if I bump into you, we better not constructively interfere, right? That'd be really, really strange. I do not want to morph with another human being, right? And certainly I don't want to run into somebody out of phase and then just completely disappear, right? So matter doesn't do that, right? But waves can do interference. Another thing that waves can do that matter can't do is called diffraction. So diffraction is basically, the bending of light around a barrier. So diffraction kind of works like this. If let's say, I'm in this classroom and I open the door, even though people in the hallway can't see the lights in here, the source of the light, they can still see the light coming out, right? Streaming out of the door. That's diffraction because the door's bending around the obstacle of the walls in this place and coming out, right, into the hallway. Matter can't do that, right? If I throw a ball, right, which is a piece of matter, this direction, it's just gonna run into a wall, right? Because there's a wall right there, right? And it can't pass through. But if I have a light bulb right here, it can definitely stream through the hallway, right? Through that open doorway into the hallway. So that's what's called diffraction. So this is how it would be represented. Okay, let's say you have a barrier with a slit. The wave crest coming in this direction can get bent, and then you get these diffractive waves here. Okay. Whereas if I would try to do this with a particle beam, right, only some of the particles will pass through the slit, right, while other particle beams are going to be stopped by the wall. Okay, but for a wave, all of it will just bend around these barriers and it will just come through this slit, right? And we can see this too. Let's see if I can find a good video to show you guys diffraction and interference. Okay. I did find a video. But let me explain this slide first so that you guys can understand this video. So now if you have a barrier and you have two slits, okay, what happens is the light will get diffracted through both slits, right? One light source can get diffraction through both slits, and then these interfere with each other to form a really cool diffraction pattern. The diffraction pattern is coming from basically the path length difference between the two diffractive waves. So that if you have a path length difference that is lambda over 2, 1/2 of the wavelength, then you get destructive interference. So you see black spots, right? But if the path length difference is so that it's equal in path length, then of course you have constructive interference, and therefore you have the white spots. And so you have alternating dark, white spots due to destructive interference, constructive, destructive, constructive, right? Interference of these two diffractive waves. All right, so let me show you that cool video.
Behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same.
And then they go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot. Now, there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously, they're going to meet up.
Okay. So as you guys can see, right, in the video, that pattern of dark light due to destructive and constructive interference. Very cool, right? So obviously, matter doesn't do this, right? Like people don't do this, marbles don't do this. The only thing that does this, right, are waves. Okay. Or at least big particles don't do this, right? We're gonna see what happens with the electron, which is really interesting. Okay, so let's go to the photoelectron effect. So this is the first experiment by Einstein that showed that light is particulate, right? Because before we thought light is only a wave, and it's not particulate. Particulate means, you know, it can be counted, right? It can be picked up and be like 1, 2, 3, 4. Just like a marble. You can be like, oh, this is one marble. You can see distinct boundaries around marble so that you can count it, right? A light, you can't do that. Where's the distinct, where's the boundary? Right? It just comes as a stream of, you know, light, right? So that's why light wasn't, you know, considered to be particulate. But this was the first experiment where it showed that light can be particulate. So, AKA the beginning of quantum physics, right? The discovery of quantum physics. Okay, so how does the photoelectric effect work? So the experiment, this is how it was set up. There's a metal surface, and inside metal surface is a bunch of electrons, of course, right? And so if you shine, you know, enough light, you know, what people found is if you shine light, you can emit electrons, okay? And the emitted electrons can be, will be passed through a wire so that you can measure the current, which will tell you how much, you know, when the electrons are coming off of the metal surface by this current meter, okay? So what they found is that there has to be a threshold frequency in order for the electrons to get emitted. So, you know, one theory of thought was, well, you know, maybe the metal surface could save up light. So if you just shine light at it for a really long time, it can save it up, just like you save money, right? And then that it will have enough energy to emit the electron. Well, that wasn't true. If you didn't shine light of the correct frequency, so here's frequency of light on the x-axis, right? If you shine it at some other frequency, it will not eject, okay? So you have to have a certain frequency of light for the electron to eject. Okay? Um, and that's because the electron is inside of the metal at some frequency. And it has to meet that frequency in order for the electron to eject. Okay. So that allowed Einstein to explain that light energy was actually delivered in what's called packets, photons of certain energy. Okay. So the energy of that certain photon of light is going to be directly proportional to its frequency. So the equation is E is equal to h nu. Of course, the higher the frequency, right, the higher the energy. The lower the frequency, the lower the energy. And Planck's constant, just like any other constant, is this number, 6.626 times 10 to the minus 34 joules per second. It never changes, right? So like any other constant, it's always going to be a certain number. And that certain number for Planck's constant is this. It's probably on your conversion sheet. Okay. So whenever you see H, right, that's what you're going to plug in, all right? So now that we know that E is equal to h nu, let's go to the board. We can derive, right, since E is equal to h nu, but we had an equation earlier, right? C is equal to lambda nu. And so if you solve for nu, it's C over lambda. So E is also H times C over lambda, right? If you plug, sorry, this in for nu, right? Because this is equal to nu. So you have two equations here that you can solve for energy, okay? So in that photoelectric experiment, there was only a certain frequency of light that ejected the electron because that met the threshold frequency in order to rip the electron from the metal surface. And that energy is proportional to the frequency of light, right? Or also the wavelength, okay? And so that's how we get these equations. Now we can calculate energy if we're given frequency and we're giving wavelength. And you can see that frequency is directly proportional to energy, right? So the higher the frequency of light, the higher energy it is. The lower the frequency of light, the lower energy it is, okay? And energy is inversely related to lambda, right? Because lambda is in the denominator. So if the denominator gets large, that means you have long wavelength light is lower energy, right? And shorter wavelength light, so your denominator is smaller, is higher energy. Okay, and that makes sense because remember, frequency and lambda are inversely related to each other. So that and since frequency and energy are directly related to each other, that means wavelength is also inversely related to energy. Okay, so those are your two equations, right? By the way, these are on your equation sheet as well. So, of course, you don't need to memorize it, right? You just need to know how to work with it, okay, and when to use it. Okay, so from the photoelectric effect, Einstein described light as coming in these packets. So just by the way that he describes photons is then a kind of like particulate because you're counting photons, right? And so that was the first instance we found out that light, kind of behave like particles a little bit, right? Okay, so that one photon, right? It just needed one photon, not many, just the one photon that met the threshold frequency sent the electrons flying off because it met the binding energy of that electron, right? It met or exceeded the binding energy of the electron. And so the electron came flying off. Now, if they were to irradiate that metal surface with a shorter wavelength, meaning more energy, well, the electron will absorb the amount of energy it needed to escape from the metal surface, but then that extra energy would get converted to kinetic energy. So it'll fly off with, a higher speed, the shorter wavelength that you have, right? So it'll just take that excess energy and it'll fly off with faster speed. So here's a question, right? Just a concept check for you guys. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? Okay, so you guys should know this, right? You know the electromagnetic spectrum. Yellow light, ultraviolet light is higher energy than yellow light. So the electron will get ejected, right? And it'll use that extra energy as kinetic energy to fly off the metal surface faster. So the answer would be C. Electrons would be ejected, and they would have greater kinetic energy than those ejected by yellow light. Okay, C. Okay, let's do this problem together. A nitrogen gas laser pulse with a wavelength of 337 nanometer contains 3.83 millijoules of energy. How many photons does it contain? Okay, write this down, and then we solve it. Lambda is 337 nanometers. Contains energy E is 3.83 millijoules. And it's asking for how many photons? Okay. So again, we're asking, we had that equation earlier, right? E photon is hc over lambda. I'm choosing this one because it gave us wavelength, so I need the energy equation with wavelength in it, right? The other one, E is equal to h nu, wouldn't be useful here because it doesn't have wavelength in it. Okay? So we are being asked to solve for how many photons does it contain. Okay, so the energy of the photon is given to us here, but remember we need to change this to joules. Right? Anytime we have energy, right, it should be in joules. Right now it's in millijoules. So we're going to divide by 1,000, right? 1,000 millijoule on bottom, 1 joule on top. So that's going to be 3.83 times 10 to the negative 3 joules. And then we need to figure out what the energy of just one photon is. So we can plug it in. H is 6.626 times 10 to the negative 4 joules times second, times the speed of light is 3.00 times 10 to the 8 meters per second. Right? Divide by lambda. So lambda is in nanometer, right? We need to get it to meter. Okay. So we have 10 to the 9 nanometers on bottom. 1 meter on top. That'll give us 3.37 times 10 to the minus 7 meters. So I'll plug that in down here. Okay. So the energy of just one photon is 5.899 times 10 to the minus 19. Okay, that's per one photon, right? Per one photon. Okay. But now in that pulse of light, there's this many joules. Okay, so this was in joules. So there's that many joules, so we want to find photon. Okay, so we'll start with 3.83 times 10 to the minus 3 joules. And we got to put photon on top, right? So for one photon, there's this much energy in it. So if we have this many joules, (6.49 times 10 to the 369). Well, 15 photons. It's a lot, right? 6.49 times 10 to the 15 photons. Okay. Okay, let's do this problem together. Arrange these three types of electromagnetic radiation: visible light, X-ray, and microwave in order of increasing wavelength. Okay, so A, increasing wavelength, B, increasing frequency, and C, increasing energy. A, wavelength. B, frequency. C, energy. And what we have is visible, X-ray, and microwave. All right. Okay, so A, we have to do increasing wavelength. Remember, increasing means going smallest to largest. So what's the smallest wavelength or the shortest wavelength? Shortest wavelength, remember, is highest in energy. So the highest in energy of all these lights, X-ray, right? You guys should memorize that electromagnetic spectrum, okay? So remember, how does it go? Radio, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, right? Okay, so shortest wavelength, highest energy is X-ray. Okay, followed by what's the one with the longest wavelength? That'll be microwave, right? So then visible comes next, and then comes microwave. Microwave have the longest wavelength, right? With the lowest energy. Okay, B, frequency. Okay, so the lowest frequency one must have, remember, it's inversely related to wavelength. So the lowest frequency must have the longest wavelength. That's microwave. Or the lowest energy, right? So lowest energy, medium, and then highest energy, or shortest wavelength would be, or sorry, yeah, so X-ray would be the highest frequency, right? And highest energy as well. Okay, and then we got energy. Obviously, energy is going to have the same order as frequency, right? Because the lowest frequency will also have the lowest energy. So it's also microwave, followed by visible, followed by X-ray. Okay, so from smallest to biggest, right? Increasing. Okay, let's move on. Next topic is spectra. Okay, so what is spectra? So when atoms or molecules absorb energy, this energy is often then released back as light energy. So we see this in fireworks, neon lights, etc. So in neon lights, basically why it's called neon light is because the gas inside these bulbs are neon. And of course, neon has electrons, right? Everything has electrons. But this gas gets excited, right? You turn on the electricity, it gets zapped by energy, and the neon absorbs its energy, and the electrons basically jump up in energy level, and then when it comes back down, it releases lights. And so that's why you see, this neon light. And so this is what we call an emission spectrum. The emitted light is then passed through a prism, and it gives you this pattern, this very unique pattern, and it's unique to the atom or the molecule. And so this is called the emission spectrum. And it's almost like a fingerprint. If you have an emission spectrum, so you can probably figure out what that atom is. So an emission spectrum you're going to see is non-continuous, so it's not like the rainbow. The rainbow is continuous, right? The emission spectrum is discrete, it's not continuous, and it's like a fingerprint. It can be identified to, to an atom, right? So here's an example of 3 lamps emitting 3 different, color combination. So we have a mercury lamp on the left, helium lamp in the middle, hydrogen lamp on the right. Notice that the light that's emitted, they all have different colors, but it's not a pure color. These lights that are emitted are actually a mixture of the colors. So the mercury has this sort of blue, right? This purple for the helium, and then the hydrogen has kind of like a reddish to it. But if you pass it through the prism, let's say you take the hydrogen's color, right, this color, and you pass it through a prism, you'll see that it's actually a composite of 4 lights. 2 in the blue-purple region, okay, 1 in the bluish region, and then the other one in the orange region. Okay, so we call this the hydrogen emission spectrum, and it is unique to hydrogen. No other atom will have this pattern of color. And if you really, you want to, you are able to go in and actually identify these as whatever wavelength this is. And so it is really unique, right? To this atom. Okay, here's an example of the helium spectrum. So helium has 2 electrons, right? And so it has, a more complex emission spectrum. Barium has even more electrons, right? So it has even more lines. And if you compare it to the white light spectrum, this is continuous, right? You see every single one color, every single color, and every wavelength, whereas the emission spectrum, you only see lines, right? That corresponds to certain wavelengths or frequency. You can do this in a flame test too, so this is really cool. We're going to do this in lab one day. But for, sodium, for example, if you put it in a flame, it will give off this, characteristic yellow color. If you put potassium in there, it's kind of like yellow, but also has like a purple tint to it. Lithium gives off this characteristic red, magenta color. Barium gives off this yellow with a tinge of green in it, right? So each atom gives off like a distinct band, right? A distinct emission spectrum. Here's the spectrum for mercury, and as you can see, the emitted spectrum, so this is emitted light, is what you would observe with your eyes, right? If you go and look at the absorbed spectrum, where you have the colors of the emitted lights, you have an absence, right, of absorption in the absorption spectrum. That's where it's absorbed and where it's emitted, right? Okay, so how do we explain the hydrogen atom spectrum? So Bohr was the scientist that came up with the model for the hydrogen atom to explain why you have these certain energy levels. And so he explains it as in the hydrogen atom, there are these stationary states. And these stationary states are like fixed circular orbit for the electron around the nucleus, because the hydrogen atom only has one electron, right? So the higher the energy level, the farther the orbit is from the nucleus. And when the hydrogen electron is in the first orbit, it's called its ground state. Okay. So this is what that looks like. Okay. So you have this inside the hydrogen atom. Here's the one proton, right? Around it are these concentric orbits where the electrons can be. And they're numbered, from the inner to the outer, right? And it's equal to 1, 2, 3, 4, 5, 6. As you go further away from the nucleus, you are higher in energy, right? Because the potential energy, right? Because the electrons are negatively charged. So when it is closer to the nucleus, you have lower potential energy because they're attracted to each other, right? But it will take energy to take the electron further away from the nucleus. And so that's why you have higher energy as you radiate out from the nucleus. So he explained the reason why you see those 4 colors for the hydrogen spectrum is that when the electron in its home state of n is equal to 2 gets excited because it absorbs energy, it gets excited and it can jump to a higher energy level. So let's say that it absorbed enough energy to jump to the n is equal to 3 level. Eventually, it will have to come back down to its home state, okay? So the electron jumps to the n is equal to 3, and when it falls back down, it releases energy, right? And that energy it releases is corresponding to how far it falls, right? The energy corresponds to how far it fell. So it fell from the n is equal to 6, it falls with greater energy, and so the light emitted will be of higher energy. So it falls from 6, it will emit purple light because purple light is higher energy. But if it only falls from n is equal to 3, right, then if the energy gaps is shorter, it's lower energy light, and so you see red, okay? If it falls from n is equal to 5 back down to 2, then you get blue, right? And if it falls from 4 to 2, then you get green, okay? Because that's lower energy than from falling from n is equal to 5, right? So he was able to actually explain hydrogen's 4 lines by using this model. And then Rydberg came along and came up with an equation to actually correctly predict the wavelength of the hydrogen series. And so the Rydberg's equation is 1 over lambda is equal to r, the Rydberg constant, which is written here. And by the way, guys, you can have this Rydberg constant. Check to see if it's on your conversion sheet. It should be. If not, you can write it down, okay? So write that down. That's Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So n1 squared would be the final state, and n2 squared is the initial state. So where it's falling to and where it's falling from, okay? So I would rewrite it like this, actually. One over lambda is equal to r times 1 over nf squared minus 1 over nx squared. I think that's easier to read than, n1 and n2. So just see what the final state is minus the initial state. And you can get the wavelength for the transition. Okay. So let's see. Let's stop there for now. That's about half of this chapter. So I'll meet you guys back at the next video to complete chapter 8. I'll see you then.